So welcome back. Let me make sure I record this. Okay, so today is our first time giving the lecture about optimization. So let me do this. Okay? So let me create a new one. Okay, so let me give you a little review about last time. We want to minimize a function subject to several constraints. So this is the objective function. This is so-called inequality constraint. This is equality constraint. And this is your design variable. And this is so-called the subject to. Okay, so for optimization, there are three important things. Usually we will say there are three things. One is, let me change the color. First important thing is objective function. Okay? Second thing is your design variable. And the third thing is constraint functions. Okay? The three important components for optimization. Without those, you didn't describe the problem properly. Okay? For today, we are covering unconstrained minimization problem. Okay? Which means I'm only doing minimizing f of x. And also, I'm choosing the most simple kind of problem, a 1D problem, one-dimensional. So this is only one-dimensional. There's no x1, x2, just x. Okay, so one example. Can you do this? Something like that. I want to teach you a way to solve for the optimal solution without making a guess or without using some other mathematical background to find a solution. This is a polynomial. The solution can be found very easily. But if you are solving a different problem like this, something like this, it's harder to know what's the position that gives you the smallest function value. You need to do some math. Okay, so when the problem that can be easily solved, maybe you don't even need to do optimization. You can, like last time, someone, I think remember it's you observe the math function in your mind. You kind of know, okay, there is a minimum point. But if I give you a function that is more complex, then you don't know where is the solution. So today we will teach you how to find a solution with a systematical way. It's a kind of procedure. Okay? So the method I'm going to use is so-called the Newton's method. So Newton did a lot of things in his career. And one thing he did was to teach us how to solve optimization problems. So the idea is that if you have a problem, we will approximate the function as a second order polynomial. Does anyone know how to approximate a function by second order polynomial? There is a famous method to do that. How to approximate a function, something you learned in calculus, by a second order polynomial. Monomial. If for Taiwanese, it's 多项式 is polynomial. You know polynomial, right? Something like this. This is polynomial. Second order, because cubic. How? Say again? Yes, exactly. Thank you. Taylor expansion. Okay. So we are going to do a second order Taylor expansion. So second order Taylor expansion. So I'm not sure if everyone remembers this. So a function equals to this. If you still remember, that's the second order Taylor expansion, okay? And this is your expansion point. Okay? Why do we do this? Because for a second order function, there is always an extreme point. So for second order polynomial, f prime equals to 0 guarantees extreme point, right? This is what we learned when we were, I don't know, college or high school, right? So since we are solving a minimization problem, oops, don't do this here. We're solving a minimization problem. So we are sure a function has to be like this. Okay? So there's maybe I should draw the coordinate somewhere. Okay? So there's definitely a minimum point. The extreme point is right there. So what we need to do next is to follow this idea. We can just take a first order derivative and make it 0. Then solve for this, that gives you the extreme point. And the extreme point will be your minimum point. That's what was derived by, actually, I guess many mathematicians knows about this, but this method was called Newton's method because he taught us how to do it in a iterative way. I will show you how to do it in an iterative way. So then let me continue to take a first order derivative. So now we need to do this, f prime of x. So the result would be f prime plus x minus x0 times f double prime of x0, right? And we need this function to be 0. So we need to solve for this, solve for x0, and x0 will be the extreme point. So solve for this. You can rewrite this equation into the following. You can say x minus x0 equals to negative f prime of x0 over f double prime, right? So you realize x equals to x0 minus f prime of x0 over f double prime of x0. You realize there's an equation. So can we just use the equation to find the extreme point? Yes, this is the equation. But when we do that, that is only the minimum point for that second order approximation. That is not the true solution yet. So what happened was, if you have a function like this, so this is x, this is your f. If you have a function like this, okay? And let's say you have an initial guess. This is an initial guess. And what you're doing is you will be evaluating the slope right here and the second order derivative right there, like something similar to curvature. Then you will make one approximation based on these two information, and the approximated function may look like this. This will be the second order Taylor based on approximation at x0, right? Then you will apply the equation right here. You will then determine the extreme point. This is basically the mean point. But that's only the mean point of that second order Taylor expansion. So what you can do next is to use this new point as another round of Taylor expansion. So maybe in the second round you will have another approximation. It may look like this. And then you hope at the end you will get a newer mean point based on the second round of your approximation. So do that again, you may have another approximation. It may look like this. So by my drawing, it looks like you are getting closer and closer. Does it guarantee that you will reach to the mean point? Sometimes yes, sometimes not. Okay, so if a function looks like this, if a function looks like this, it's obvious that there are multiple local minimum points. Then you can get trapped. For example, this is your initial guess, and you are moving like this, and you find this point using this approach. You have no idea there is an even lower point somewhere far away. You have no idea because you have never been there. By this Newton's method, you are just moving at the local position. So it will stop because over here your f prime equals to 0. You know this is an extreme point. You cannot find a better point. You cannot find a lower point. So in this case, Newton's method doesn't guarantee to give you minimum point. Okay, so if this situation happens, we call this point local minimum. So Newton's method is a kind of method so-called a gradient-based approach. Gradient-based approach. Usually, gradient-based approach, like Newton's method, guarantees local minimum. But it doesn't guarantee so-called the global minimum. Okay? Sometimes you want to find the global minimum. Then you need to find a different way. In the second half of the course, there is a kind of method that introduces random process. It will randomize the way you search for solution. So basically, your searching point will be jumping around inside the design space. If you're lucky, you may bump into the area that has the global minimum. Then you can find your global minimum. Okay? And there are some other strategies. For example, they will randomly start the gradient-based approach. So if they randomly start, this is a random initial guess. This could be another random guess, right? So starting from these two random guess, the second one could give you global. So sometimes in order to find the global minimum, they start their optimization with different guessing points everywhere in the space. And from all those initial guesses, they run gradient-based approach. So if they are able to distribute the initial guess among the entire design space, maybe they are lucky enough they can find the global minimum. Okay, so that's the idea. Now, I mentioned about the iterative, so-called iterative, or this is adjective. The noun is so-called iteration. Okay. For Taiwanese, it's called 迭代. It's like a plug-in into the equation multiple times. Okay? Then there's a term so-called iteration. And if you want to use it as a adjective, then it's use iterative. Okay? So if you, in this approach, you realize plugging into I solve the problem multiple times. I use the solution for one particular time as my new start for the next time. So I repeatedly doing this until I cannot improve. Then I stop. Okay, so that's so-called iteration. Now I'm going to teach you how to do this in a systematical way. So sometimes we call this a solution process, or just a optimization process. In research paper, you can use those terms, that's fine. Or you can just call it a flow chart. Okay, basically, the way you execute your iteration. Now I'm going to show you how to do it. So initially, you have initial guess, some x, and here I'm gonna call this k equals to 0. So what is k? K is so-called the iteration number. Okay? And k, in my approach, k starts with 0. So you make a guess. K0 is a number you guess. it doesn't matter which number you guess, okay? If you have a poor guess, you may get a poor result. But theoretically, if you want to use optimization, you have no idea how the function look like. So all you can do is to make a guess initially. Okay? I will solve a problem later on, but I want to show you how to solve this kind of iterative approach by this diagram. Okay, next. For Newton's method, you need to solve for f prime of xk and f double prime of xk. So now use xk as your basically the expansion point. And inside the Taylor expansion, you need to know f prime and f double prime. That's why you need to know these two numbers at this point. So get those two numbers. What's next? Apply Newton's method. Xk plus 1 equals to xk minus f prime of xk over f double prime of xk. Oops. So basically, this equation was derived by Newton. It tells you, okay, do this. And the k plus 1th x will be determined based on the kth x. K plus 1th x will be determined based on kth x. So that's how this approach was about, right? You start with an initial guess, you make a second order Taylor expansion, use Newton's equation to give you the extreme point, basically the lowest point. And then we will move on to the next iteration. But before we move on, we need to know, are we done yet? So there's an important procedure right here. It's a kind of function check. So we call this convergence check. Okay, a kind of convergence check. What does convergence mean for Taiwanese? It's called Solian. Okay, if converged, then we stop. We like to use the term converge. Okay, so if yes, then your optimal solution would be the last solution you had. Okay? How about no? If it's not converged yet, then you go back to here. So if the convergence check tells you, okay, not yet converged, then it's no, then go back. But when you go back, you need to do one thing. K equals to k plus 1. So you advance k by 1. So by this, this is the complete solution process of Newton's method. You have an initial guess, k starts with 0. First, evaluate f prime and f double prime. Apply Newton's equation. Check if it's converged. Not yet. Go back. But k plus 1. So initially k was 0. So now when you go back, k becomes 1. Then do the same thing again and again until you converge. But I haven't tell you what's the criteria for convergence, right? So now I'm gonna tell you, so-called convergence criteria. Or sometimes people say termination criteria. So terminate, what does terminate mean? Everyone knows the movie Terminator, right? To finish. So sometimes we call termination criteria means when do we stop, okay? So the criteria, there could be many criteria. You can define your own criteria. There's no rules. I should say there are some recommended criteria to use, but you can choose your own one. Sometimes this is very important, because if you choose the criteria poorly, you may get bad results. So in a paper, if you write a paper about optimization, you want to describe how you got the solution, you better describe how you determine the convergence criteria. You need to tell the author how the process terminates. Otherwise, other people cannot duplicate your research results. Okay, so for many times, people may forget to describe the convergence criteria. Okay, that's very important. And of course, if for your paper or your thesis, if optimization is not very important, it's just a very small procedure for your entire research. It's not the main contribution. And maybe you even use MATLAB to solve for you. And for MATLAB, it has default setting. You can just say, okay, I use MATLAB F-min-con with default setting. Because you didn't contribute on choosing the criteria or parameter, then that's fine. But if you are someone from a lab, you have to do it. Because I'm the professor who works on optimization. I care about how my students describe the way the optimization problems are solved. And I encourage for all other students who are trying to use optimization in your future research, you can learn how we describe optimization and then how those are solved. Now, one possible convergence criteria could be the difference between the latest solution and the previous solution has to be smaller than a small number. So if this Newton's equation gives you a new point, but it is so close to the earlier point, that means you didn't find a newer point. Okay? So how do you prove this? If you need a proof, okay? For Newton's equation, if the difference between those two are already smaller to a very small number, very small, okay? Then you can plug in what you had from the Newton's equation. This minus that would be negative f prime of xk, f double prime of xk. That means this must be very small, right? So that implies this f prime could be very close to 0. So if this is happening, then based on Newton's method, we believe it's the extreme point. Okay, but how do you prove whether it's truly the local one? I think I'm not a mathematician. I don't know how to prove it. I cannot say it's the proof. I can only say to check, because I didn't truly prove this is a solution. I just use it to show you why this criteria works, but I didn't truly prove it like a mathematician. So I shouldn't say it's a proof. I have to say, let's check. Because if I want to truly prove, that's another story. I need to make sure for for all kinds of functions based on certain definition, this guarantees the optimal. But then I need to check a textbook and then try to explain it in that way. I don't think I can do it right now. So I plan not to do it. Okay? So you can only trust me for now. But if you really want to prove, hey, under what proof this procedure works, you may need to find some research paper, probably very, very old, 19-something or 18-something. There must be some kind of proof, but I'm sorry, I didn't prepare those. Because for engineers, we don't really care. Okay, this is a kind of criteria that you can use. Okay? There could be some other criteria that you use. So another kind, let me just call this criteria 1, criteria 2. You can check the function value. You can check whether the function value has improved, has reached a converged situation. So when the function value of the new point is so close to the function value of the previous point, then probably you should stop. So in what situation you could see this? So if you have an equation that is very flat at the bottom, so you start from here and Newton's method let you move, and when you are very close to the bottom, sometimes you move a little bit, but the function value has no change. It's so flat. Maybe both of them are minimum. Their function value are equally small. So sometimes people believe you can stop. So if you choose this second criteria, if you use this second criteria, you may reach to a very flat position, even your x moved a little bit, but your function value has no change. You can stop. Okay, so this is a second kind of criteria that you use. How about the third kind? Use both. So both criteria needs to satisfy, then you stop. So you not only limit, I should say, not only stop when you see no movement for x, but also see no value change for f. Then you stop. So if you use both criteria, maybe the iteration process will be longer, because in this particular situation, you are already in a very flat ground, very flat, but your x is still moving. So in that case, if you have both criteria being used, optimization will continue to move until there's no movement. So you will see more iterations. So it really depends on how many iterations you want. So there's also another criteria, maximum iteration number. So you stop until your iteration reach to certain value, then you stop. But if you use this, you need to be very careful. Sometimes you set up, for example, maximum iteration number equals to 10, but it didn't really converge. Sometimes it will converge at the 15th iteration. Then you are just out of time or out of resources, out of budget to do more. You have to stop. So one obvious example is car making company. I know about this is because when I was in USA, I knew a lot of researchers who works in car company, Ford company. So in Ford, F-O-R-D, you know the brand, right? Ford. So many engineers works on optimization in Ford. We met in international conferences. We had, they told us a lot of stories about how they truly make cars inside the company. So every time they make a new car, new model, they will truly crash the car into a wall to test whether the passenger survives. So it's like a car crashing test. But think about how much a car could cost. So it could be, my car is more than 1 million Taiwanese dollar. So for them, if they make a car, maybe the cost is 1 million. They basically crash the car into the wall and then throw away $1 million. And actually to set up that kind of test and to make a testing car like that, the cost is definitely greater than 1 million. It's not just cost for making the car, it's a lot of cost. So for Ford, for the company, every time they make a new model, they cannot crash 100 cars. The maximum number of cars they can crash is 5. When the 5th car crashes into the wall, they have to sell it. Otherwise, they will be losing money. So they prepare a budget to crash it, to crash a car. So every time they crash the first car, they see some inappropriate design, they redesign it. But how did they redesign? Optimization. So that crash into the wall is like evaluating some kind of function everywhere inside the car. They use the response, the result, to see the strength of the structure, balance of everything. Then they use all those experimental data to redesign for a second car. There are thousands of design variables inside the car. So it's sometimes iteration number cannot be too large. You don't have infinite number, I should say, you don't have infinite time or infinite resource, infinite budget to do optimization. Sometimes I see students work on optimization and let the computer run. It's already reaching thousands of iterations, it's still solving it. Stop, please. Something must be wrong. If you cannot, for students or researchers, if you solve for optimization problem with iteration number greater than 20, something is wrong. It's not converging, it's not working. Then you may want to stop, go back to the problem and maybe redesign a little bit. Because if you allow the solver to do this iteratively, what if it will stop at 1,000 iteration and it's gonna take 1 month to solve? Then don't do it. Don't waste your time. Go back and then check what's wrong and then try to solve problems more efficiently. So based on my experience for graduate students, if a problem can only be solved, if the problem cannot be solved within a week, probably you need to redesign. Unless you are sure. I know, for example, someone is doing simulation. It's taking a long time, but and for example, the simulation is gonna take 2 months to complete, and you're confident. After 2 months, you only need to tune the parameter, for example, 2 more times. That's 2 times 3, 6 months. You're sure after 6 months you can get something so so worthy, so priceless, and it's good for your thesis, and then I think you can do it. But if you're not sure, then whatever you're solving may be costing too much time. Then you need to tune your process. I have one student. He is doing some experiments. He's using some kind of polymer and with some 3D printing machine. So he printed some material and applied some polymer. So it's a structure with multiple kind of material. After that, he needs to remove some of the material from that composition. So what he needs to do is to dump this into some kind of solvent and put it inside ultrasonic vibration machine. So using that vibrational force to dissolve the material more quickly. So after first trial, he told me that vibrational material removal process took him something like 2 weeks to remove. Then that means for every solution right here, it takes you two weeks. And you may get a poor result. So when you move on to the next design, it's a month later. So you need to evaluate whether it's the right way to do experiments. So from optimization, you can learn how you make a decision in your experiments. Because you are actually doing optimization. You're just not doing it by Newton's method. For every research, initially you don't know the parameters. You just pick up some numbers. And at the end, either it's an experiment or a simulation, you get some results. Based on that, you of course will make some changes. Okay? So it's whenever you make a change, you will be moving toward the solution maybe slightly closer. But if you're unlucky, you could be finding a solution far away from your solution, right? So for optimization, you need to set up your criteria more effectively. You want to make sure this criteria is going to help you. It doesn't give you a hard time so that it's going to converge for a month. Then you need to change some parameter in here. Okay, so I just want you to use this as a guidance for your own research. Now let's try to solve a real problem. So let's try to minimize, for example, 6x, maybe the fourth, plus, I don't want to use a cube, so maybe 3x squared, maybe minus 5x, okay, something like this. I hope it has a solution. Okay. Maybe I start with something easier. It's okay. Let's try this. So I don't know the solution. Let me have an initial guess. So x of 0 equals to, let's say, 2. Okay, I have no idea. So my f prime equals to 24x cubed plus 6x minus 5. F double prime equals to, you know what, I don't like large numbers. So let's eliminate that. So 4, easier. 12x cubed plus 6, right? Okay. So you need those all the time. So first you need to evaluate f prime of x0. So just plug in. So 4 times 8 plus 6 times 2 minus 5. So I'm solving by hand. So 7, 30. When I solve by hand, sometimes I make mistakes. So if I make mistakes, you can do better. So 2 cubed 6. So 48 plus 6. That would be 54. Okay. So x of 1 equals to x of 0 minus, let me do it slowly, f prime of x of 0 over f double prime of x0. So this tells me 2 minus 39 over 54. Then I need calculator. Or, let me use this. So 1.28. Okay. Next, I need to check x1 minus x2, not 2, minus x0. So it would be 2 minus 1.28. So it's actually 0.72. Oh, I haven't set up my criteria. So I want this to be smaller than 10 to the power of negative 3. So it's still larger than 10 to the power of negative 3. I want this to be my criteria. So when this happens, initially k equals to 0. So now x advanced by 1. Now x equals to 1. I will be continuing what I'm doing. So I will now k equals to 1. I will be evaluating this and this. Yeah? Sorry, blocking the way. Thank you. So I will be doing this. Because x advanced by 1, by the flow chart, I need to evaluate this. So now let's try to do it. This is 1.28, right? So I can no longer solve by hand. I need to do it by calculator. 1.28 cube. So this is 11.1, and then 1.28 squared plus 6, 25.7. Okay. Am I doing? Okay, I think yes. So x2 equals to x1 minus, let me directly write down. So 1.28 minus 11.1 over 25.7. So 1.28 minus 11.1 over 25.7. So 8.5. Something like this. Then you can then check the difference between the new one and the last one, 1.28. So this is 1.28 minus 0.85, 4.3. Okay? So from here you can do something. It's not yet converged, not yet, you need to continue. But over here you can try to compare about the difference right here and the difference right here. So by 2 iterations, you already see the difference is getting smaller and smaller. If I do one more, I hope the difference is getting even smaller. So eventually, I should be able to find a solution. That's the idea. Okay? Actually, that's how you do it, by Newton's method. Just keep on doing until you get a even smaller value. Okay. So I will show you how you can do this by MATLAB. If you are not familiar with MATLAB, you want to use Python, C++, it's up to you. But for myself, the most effective way of programming is MATLAB, because I learned MATLAB when I was a student. Okay, I didn't learn Python and C++ when I was a student, so I like MATLAB more. But MATLAB is the operation speed is slower than C++. So if you are doing a project, usually your professor will ask you to work on C++ or Python. Okay. Any questions at this point? Should be quite easy, right? Because it is one-dimensional. Let's try to solve it by MATLAB. Is it rolling? Yes. I need to turn off this. Okay. Oh, my computer is almost out of battery. The charging is not enough for how I operate. So I may lose this very soon. Only 18%. Well, if I lose it, then I cannot show you MATLAB. I can only continue with my iPad. Don't do this right now. Taking too much time. Okay, let me restart. Okay. I need to program this very effectively, otherwise I cannot complete in time. So let me just start a script. Okay. I cannot program with my microphone on, so I will just speak up. So usually I will say clear, CLC means, clear means clearing the memory, CLC is clearing the screen. So now I want to solve for a function f, and I will use, I use symbolic. I like symbolic. So symbolic means you can have a function that looks like an equation in MATLAB. So now I'm solving for x to the fourth
plus 3 squared minus 5 times x. Okay, so f is a symbolic function right now. I'm going to have my variables using capital X. And 1 means, let me start with k. So k equals to 1. So over here, xk. I'm gonna have an initial guess that would be 2. Now I'm something called error. That's the value of my termination criteria. Let me set up a large number so it will, in the while loop, it will not finish. So when this error value is larger than 10 to the power of -3, I need to continue. So over here inside, whenever I'm inside, I need to evaluate f prime and f double prime. So let me just call df as differential of x. df is differentiate again. What happened? Oh yeah, df. Okay, so in the while loop, I will be solving for x of k plus 1 equals to x of k minus substitute df x using my current x over substitute ddf over x with the function value of xk. That will give me my new x. And I will update my error value will be absolute of xk plus 1 minus xk. Only difference is that in my lecture notes, I start with k equals to 0, but over here in MATLAB, variable index cannot start with 0, it starts with 1. So let's see if this works.
Professor, that should be 3x squared.
Hold on.
Okay.
Hold on. Oh, okay. Oh, x. Thank you. 3 times x squared. I'm not sure if it works. Let me see. Okay. Not sure what happened. Yeah. Debugging mode. Okay, everyone works. Everything works. So over here, does the substituting works? Yes. So error. Forget about one thing. K equals to k plus 1. Because if I move on to the next iteration and the k value didn't advance by 1, I'm doing the same iteration continuously without stopping. I'm not advancing. Okay? So this should do it. Yeah, so 6 iterations it converged. Let me show you the iteration process. So initially, I will display initial guess equals to number to string x of k. And then every time I evaluate, I will display k equals to, when k equals to a number, so number to string k, then I will comma and say x equals to number to string k of x of k plus 1. Show the function value, x value. And then I will show you the error. Error equals to number to string error. Run it. Something is wrong. I don't want this. Sorry. It has been a while. The last time I programmed MATLAB, it was, I don't know how many times ago. Okay, so over here, just like what I did, first iteration 1.28, error number 0.72. Second iteration 0.85, and then error 0.43. And if you keep on doing it, it will stop at the 5th trial. And the error is as low as 4 times 10 to the power of -4. It's already smaller than 10 to the power of 3, so it stops. So the optimal solution is 0.65. Can someone guess where the solution is when you first see the problem? I guess not. Without an appropriate optimization method, it will take you a while to find the solution. Of course, you can try to find by checking. You can check, okay, from 1 to 10. Okay, find everywhere. Then how many times do you need to find? Even you find everywhere, you just evaluate the function value from 0 to 10. And you move your searching point by 0.1. So inside 0 to 10, you search for the function value. You substitute into the function value for 100 times. That only gives you an accuracy of 0.1. By optimization, it gives you the accuracy of 0. So close, so accurate. It's a 0.01 accuracy, even lower. Actually, the accuracy is 10 to the power of -3. That order of 10 to the power of -3. So, how many times we evaluate the function? Every iteration, we only plug into the DF and DDF twice. And then, of course, it's a derivative. So it's a little different from directly substituting F. But from here, you can tell the required function evaluation times is very small, maybe 10 times, 20 times. I will tell you exactly how many times MATLAB evaluate. But before I do that, I need to teach you something about finite difference. So now I only have 7%. I want to show you something to help you understand better. I hope I can complete within 6%. So I better save the video at 1%. So I'm gonna plot the function. So easy plot F, and let me plot inside a region called zone. So zone I'm gonna define as from 0 to 10. Okay, let's see. So that's the function. That's the kind of function with a very flat bottom. Let me plot from -5 to 10. Oh, I should say F close all, function close. Not F close all. So it will replot. So you can see it has a very flat bottom, but there's a minimum right there. Okay? I'm gonna show you how second order Taylor expansion approximate the polynomial. Let me quickly do that every time over here. So capital F equals to substitute into F. I'm writing down Taylor expansion plus x minus the current x times F prime. This is F prime plus 0.5 times square of this times F double prime. This is F double prime. So that capital F is my second order Taylor expansion. I'm gonna plot it on top of the same figure. So I'm gonna say hold on. So it will plot. Okay, so let's do it. Let me just pause so you can see it. I should pause right here. I should pause right here. And do it again. So this is my initial function. And over here, I'm gonna say. So the next time, the red one is the second order approximation based on the expansion point. The orange one is another run. Third purple one. Is it a purple one? Not sure. Yes. So you can see that Taylor expansion moves, and the lower point is getting closer and closer to the right here, to the flat bottom of the original function. See, the red one was higher and further away from the true minimum. The blue one is the true minimum. And after one iteration, my solution point moved from here to somewhere right here, closer to the solution. My second order Taylor expansion is closer to the shape of the flat bottom, and it's moving closer and closer. Let's continue and see what's going on. Come on. I think my computer is almost out of battery, 5%. So it doesn't. Anyway, you get the point. Okay. So I'm gonna stop right here and then save my me video. Otherwise, I worry it will not save. And I will be using iPad from now on. So, sorry. If you have a function like this, and traditionally when you have no idea where the bottom is, the minimum is, you may be searching. Let's say, okay, there's a searching point, and you move a little, and then you search again. You move a little, and search again. You basically will be sampling your space and trying to find where is the minimum. And you spend a lot of effort trying to find the point. And if the gap you choose was not small enough, you could be having two samples surrounding the true solution, but due to that gap is not small enough, you could be missing the true solution. So you don't have enough accuracy on your solution. In that case, you need to sample more inside a region, right? And if you want even more greater accuracy, you need to keep on sampling more
near the solution. So that is not an effective way. By Newton's method, it gives you approximations of second order derivative, solve for the minimum by f prime of 0, and then using that new point, create another round of second order derivative, and then get closer and closer. Usually it's spending less so-called function evaluation. Sometimes we say function call or function evaluation. And for researchers who are trying to promote their optimization algorithm, they sometimes use the amount of function calls to compare how effective my method is. Let's say you find a new method and your method requires fewer function calls, then you can say your method is more effective, more intelligent. Okay? So that's why we sometimes need to count how many times we evaluate the function. So basically, how many times this has been done. So this is evaluating a function is just like crashing the car. I have a set of variables ready. I have chosen so many variables. That's one set of design. I crash a car and all I want is a function value. Maybe the function value is maximum deformation after a crash. So maybe what you are trying to do for the car crashing example is you try to minimize deformation after crash with a bunch of variables. You want to minimize that. And maybe this equation is a very complex equation. If you want to find the variable that has the minimum deformation for car crash, and you find it in this way, you need to crash 100 cars. Then you are bankrupt. Or maybe you tell yourself, let's use simulation. Computer is powerful. Yes, but if one car crash simulation costs 1 hour, then you need 100 hours. 100 hours is such a long time, right? It's more than a week. Not for computers. For humans, it's more than a week. So 100 hours is like close to a week. So that's also money. For time is your money, right? You only have 2 years to complete for a master, 4 years for a PhD. Every day counts. Let's say in your thesis for a PhD, you need to write 300 pages. Then every day you need to get something ready for maybe 1/4 of your page. Are you improving yourself by 1/4 of your page inside the thesis, right? So time is money. If you try to evaluate this by simulation without a effective approach, it's gonna cost a lot of resources. Now, for gradient approach, how do we count this? How do we count? Because over here, what we did was we used f prime of x, f double prime of x. If I know what the function look like, I will just solve for that math function and then get a solution. But sometimes it's really hard for you to describe some function in real life. For example, what is the deformation after crash with respect to all the variables in the car? maybe it's actually tens of equations combined together in order to truly calculate it. And even with that, you may have uncertain variables. Because when you design, like I said last time, when you design something with a certain size, in reality there's a slight variation. So in real life, sometimes the function value is, the equation is unknown. You have no idea how the equation look like. When we solve for math problems, I give you exact description of the function. But in your own research, in real life, that how the equation looks like doesn't exist, or you cannot find it easily. You cannot determine it easily. So what do? How do you solve for this if you have no idea how the function look like? So what you can do is to, in real life, you can estimate the derivatives. Does anyone know a way of estimating derivatives? Anyone knows? Something that is finite? Okay, it's called a finite difference. You guys know, right? So what is f prime? By definition, it's a limit del x close to 0, del x f of x plus del x minus f of x, right? This is a definition of first order derivative, right? But you need this increment to be infinitely small so that the value is exactly the same. So what finite difference did was, this is infinitely small, but I'm choosing a small number that is that you can observe. It's not infinitely small. So f prime of x could be approximated by same equation, but this time, this is just regularly small. Regular small. Just a regular small number. Not close to 0. Then it's a so-called a finite difference approach. And of course, we call this the forward scheme. You don't really need to do forward scheme. So what does that mean? Over here, this is x. This is x plus del x. Here is x minus del x. You're trying to evaluate some function. Over here, you want to know what is the function value of f prime. And what you did was, you evaluate the function value right here, and you evaluate the function value right here. This guy minus this guy, so basically the height. And this guy over this guy minus this guy. Basically, this is the width. So what you're doing is height over width, basically the slope. This is just an estimation of the slope. Okay? But can I only estimate the slope with these 2 points? Maybe not. Maybe I can use these 2 points. Right? If you do that, then you are doing a different scheme. You are doing this. This is so-called a central scheme. Does it matter? It doesn't matter. Will those be the same? No, they will not be the same. Are they close to each other? Usually yes. So it doesn't matter if you are using this one or this one, you can still estimate. It's an estimation. It's not the exact value. Okay, and if you want to use backward scheme is like this. This is backward scheme. Okay? How about F double prime? Okay? Let's do a homework. Number 1. Prove F double prime of X equals to can be approximated by del X squared okay, homework. Okay, it's very easy. You can go back to check your calculus book. You can find it. Okay? So that's your first homework. You can write down your homework and then hand in next time. Now, how do we count the function calls? So whenever for every iteration I mentioned we need to evaluate f prime and f double prime. So basically, for the optimization process, we have initial guess of xk, and then we said we need f prime of xk. So in fact, what you are using is with a small value, you can set up your own small value. And then you are going to estimate at your guessing point plus a small increment minus f of x. Here I'm using forward scheme. And then my f double prime could be estimated by your homework, del x squared f of x plus del x minus 2 times f of xk plus f of xk minus del x. Okay, so let's count how many function values did we use for this particular equation, for this particular iteration. I evaluated this once. Same value can be used over here. So let's count 1. Okay? I increase my guessing point by del x. I use that new position to evaluate function for the second time. So this is my second function evaluation. Okay? Same value right here. This is the same value. And also I move backward by the small value. So it's a small decrement. So this will be my third evaluation. So for every iteration, I need to plug into this function f 3 times. Then I can use Newton's method to tell me my function value. So next will be this. Basically, over here, do I need to plug in f anymore? I already have f prime and f double prime. Over here, there's no more evaluation for f. Just plug in. And then my convergence check. If not yet, we move it back to here, right? The k equals to k plus 1. So we will be doing this cycle multiple times. Every time is called one iteration. every iteration I use function call 3 times. I plug in f 3 times. So in the earlier example, it took me 5 iterations to converge. The total times of function call, it would be 15. I only need to plug into the function 15 times, I found the solution. With this stupider approach, this is a smarter approach. This is not a good approach. With this, I may need to evaluate function 100 times, but not getting the same accuracy. Here, 15 times. So that's why optimization could be very useful. Okay? Any questions? Now, we have to do a second homework. Solve for same problem. With finite difference. Okay? Finite difference. So earlier, when I used MATLAB, it was done by symbolic. It was an exact evaluation of derivatives. But if you use finite difference, the derivatives won't be accurate. So your f prime and f double prime will be approximations as well. So in my MATLAB code, it converged at the 5th iteration. With finite difference, because the derivatives will be a little inaccurate, it could be taking more iterations. It could be taking up to 8 or 10. So I don't want you to solve for this for too many times. So I want you to use a termination criteria. Max iteration number is, let's say 5, okay? So you will stop your solution process when you already try 5 times. So I guarantee you, if you do this correctly, the solution you get right here won't be the same as my MATLAB code. Okay? So you can try it. So there are multiple sources for the information. I have the MATLAB code, I have my screen videotaping, I have my iPad, there's a videotape right here. So from multiple informations, if you miss anything, go back and watch that. Okay? Let me see what time. Now, we still have 1 hour. Can the TA come here and take a picture? I'm going to erase it. And I want to move on to the next topic. Yeah, if you have a question, you can ask me. If you have to use Chinese, it's okay. Maybe I explain in Chinese? You guys okay? Everyone okay? Any doubts? Oh, by the way, when you do this, you can double check whether you use 3 function evaluation in each iteration. And I only want you to do it 5 times. So actually, you should be evaluating f 15 times. You're supposed to do 15 times. If you're not doing 15 times, something's wrong. Okay? And of course, if you didn't do forward scheme right here, if you are using central scheme, then you are evaluating at the half delta positions in that case, the whatever you're doing right here won't be the same as what you're doing at the F double prompt. Then you are not reusing the values. You are basically trying to evaluate at different positions. In that case, you need to evaluate F 5 times. So that's why for us, we usually like to use forward scheme because we evaluate at F, and for the F double prompt, we also use the same value for a second time. We don't need to choose a different position for function evaluation. Okay? So, are you guys okay? Now, I'm moving on to multi-dimensional Newton's method. So you may need to pay more attention on this. It's getting more difficult, much more difficult. So now we are having multi-dimensional problem, and I'm going to introduce how to use Newton's method to solve for this. So here we will have multiple x. So we use a vector to connect them. We put all the values, multiple values in different dimensions into one vector. So we still have one function, but multiple variables. Still one function, but multiple design variables. Okay? Just to clarify. Not multiple functions, still one function. So again, second order Taylor expansion. Do you guys still remember how to do second order Taylor expansion for multi-dimensional function? Maybe not. So let me show you. This is dot product, not multiply anymore, it's dot product. And this is so-called the gradient. Oh, by the way, earlier I mentioned gradient. Maybe you forget about gradient. For Taiwanese, it's called T2, right? But there's no translation for English. English is gradient is gradient. 1/2 of dot product, something called Hessian, dot product again. This is called the Hessian matrix. Okay. So, what's inside the gradient? Basically, a container of all the first order partial derivatives. And plug in the expansion point. After you do the partial derivatives, you plug in your expansion point. Okay? So what's inside the Hessian? It's a matrix that contains all the second order partial derivatives. Second order partial derivatives. Okay. Oh, by the way, plug in your expansion point. Okay. And usually this is a symmetric matrix. For most well-behaved functions, the f partial x1 partial x2 usually is the same as f second order derivative of x with respect to x1 and x2 and x1. It's hard to pronounce. It's a very long name. Usually symmetrically the same. Okay. Huh. Does anyone want to drop the course? After this, okay, I'm gonna drop. Kill me. Okay, but with this is not enough. We need Newton's equation. So the derivation actually is similar to the one-dimensional, but it's a little trickier when you are handling this. Okay, so I'm gonna tell you the solution directly to save some time. So for Newton's method, at the end, it looks like this. Minus Hessian matrix inverse dot product gradient. Luckily, I'm not going to ask you to prove it. Proving this is very troublesome. But how come you see inverse right here and it's reversed? So compared to one-dimensional, we are doing this, right? For one-dimensional, f prime over f double prime. But for multi-dimensional, Hessian is a container of all of our second-order derivatives. But a matrix cannot be placed at the bottom. You cannot do it. So for a matrix, if you want to divide it by the particular matrix, it's actually inverse and then dot product. So inverse and dot product with a gradient, mathematically is just like doing this, f prime over f double prime. Okay. Now, let's give you the complete procedure of multi-dimensional Newton. So initial guess, f of x, k equals to 0. Then evaluate the gradient and Hessian. Then Newton's equation. Then convergence check. If not, so converged, question mark. If not, k equals to k plus 1. If yes, your optimal would be your last solution. That's basically, you can see how similar it is compared to the one-dimensional one. Okay, let's try to solve a problem. This time, I'm not going to use a complex problem because I need to do the Hessian. So now I have a function, let's say x1 squared plus 10 x2 squared minus 6 x1, something like this, or plus 2 x2. Okay? So my initial guess in this time would be, it has to be a vector. So let's say 2 and 2. Okay? And along the process, I will need my gradient. So I'm gonna have my gradient for now. So it's gonna look like partial derivative with respect to x1. So 2x1 minus 6. Do it with respect to x2, 20x2 plus 2. Okay? Now, what does my Hessian look like? My Hessian look like this guy doing a partial derivative with respect to x1 again. So it's going to be 2. This doing it with respect to x2 is going to be 0. This with respect to x1 is going to be 0. This with respect to x2 again, so 20. Okay. Later on, I'm gonna need my inverse of Hessian. So my inverse Hessian always look like this. You can try it. H, oh yeah. H dot product, H inverse. At the end, it's gonna be identity. So that means that matrix is the correct inverse matrix. Okay, I got everything I need. I'm gonna start. So for the first iteration, I will have 2, 2 minus the inverse right there. Dot product, this guy, the gradient. So plugging in 4 minus 6 to 14 plus 2, right? Do some math. This is gonna be, this is negative 2, so negative 1, negative 42. Oh, I don't like, calculator. So 42 divided by 20. Oh, 2.1, okay. So it's gonna be 2.1. Right? So at the end, 3, so 0.1. Right? Should be right. And then I'm gonna do the convergence check. So this time, how do we check? Because vectors, you cannot just use absolute value anymore. Here, I'm going to use norm of a vector. So basically, the length of the vector, the difference vector. So I'm going to do this. So it's going to be 3. And then minus 2, minus 2. Okay? I'm going to do the norm of this vector. So it's going to be the norm of 1 and 2.1. So if you truly want to calculate this, it's basically a value something like this. Definitely larger than 10 to the power of negative 3. So not converged yet. So move on. Now, k equals to 1, because I advanced my k by 1. So I will be doing x2 in the next iteration. So over here, my x1 would be this guy. And minus my Hessian inverse. Dot product with my the gradient. So plugging in 3, so it's gonna be 6 minus 6. Minus 0.1, so from here, did you see something magical? this is 0, this is 0. So this whole thing is 0. So at the end, I have the same answer. Right? Because this whole thing is 0. So if I do the convergence check, it's the same point. Exactly same point. So at the end, it's 0. Definitely smaller than 10 to the power of negative 3. So converged. The solution is this guy. This is my optimal. That's it. Where's my cap? Yeah. So if you have a second order multi-dimensional polynomial in your experiment, if you use Newton's method, it will give you the solution in 2 iterations. The first iteration give you an answer, second iteration confirm it, and then done. Now, over here, we know what the function look like, so it's easy for me to do the derivative. However, if in real life, sometimes you have no idea how it looks like, then you can only use finite difference. I'm going to show you how you can do finite difference for multi-dimensional problems. So whenever you're doing one of the component inside the gradient vector, then you are doing this. You are doing a partial derivative with respect to the I variable. Then approximately you can have some small value, and over here a vector for x plus small value here, multiplying something called a normal basis, EJ. You guys know what is a normal basis, right? So EJ equals to 1. This is the jth component. So this is a normal basis. Only the jth one is 1. So use a small value multiplying. So basically 0, 0, 0, then the jth one has a del x increment. And 0, 0, 0. Okay? Minus. Yeah. So that's how you can do partial derivative of one component inside the gradient vector. Okay? How about some particular component inside Hessian? Let me find a place. So partial x. Let me use I and j this time. Okay, I and j. So in this case, let's choose the exact same increment in x1, in xi and xj. So the increment is the same. Here, trying to save some space. Okay, so f. So I need to finite difference for let's don't do the ij yet. Let's do the yeah, that's okay. Let's do the ij. So I need to move to the upper right. So plus del x times ei plus del x times ej. Okay? Minus plus del x ej. Oh, I have no space. I have no space. TA, can you take a picture of the right hand side? I need space. Okay? So maybe I can show you in the design space. X1, X2. So here is your xk point. Over here, this is like xk plus del x E1. Here is your xk plus del x E2. Over here, we need this point as well. This is your xk plus del x E1 plus del x E2. We need that guy as well. So continuing plus del x it's okay, either way, I plus f of x. Okay, so when you have off-diagonal terms for Haitian, you use this one minus this one minus this one and then plus this one divided by square of the small value. That's how you do finite difference for off-diagonal terms. This is off-diagonal terms. Okay? How about the diagonal terms? So let's take this one as an example. Okay? This one you will be doing central scheme. So very similar to the one-dimensional problem. Okay? So this guy minus 2 times of this guy, and then you need a backward evaluation. So this is minus del x E1. So for off-diagonal terms, for the ith dimension, you need the central point, you need to move forward a little bit, and you need to move backward a little bit for function evaluation for 3 positions. So the one in the front minus 2 times at the center plus the one in the back. That's for off-diagonal terms. For the off-diagonal ones, you will be using the 4 values right here. So this is the xi, xj. Use the one at over here, increment on both the dimensions, minus this one and this one, plus the one in the center. Then you can evaluate the off-diagonal terms. Okay? So if you know how to do finite difference in real life, when you have no idea what the function is, you don't know how to get gradient. Then in this case, you can use this equation. You just evaluate what's happening a little bit further, and then minus what's happening at the design point. You get that partial derivative. Okay? I think I'm not going to ask you to do this homework, not the multiple order, but later on, next time, I will teach you a different method. This is Newton's method. Later on, I will teach you so-called the steepest descent, and then conjugate gradient. I will use multi-dimensional from now on. In those methods, you still need to evaluate gradient. So in the future homework, I will ask you to solve a problem. Please use multi-dimensional Newton, use steepest descent, use conjugate gradient. So eventually you need to practice this later on, but not in this week's homework, because this is just homework 1. Later on, you still need to master how to do this. And you will be having take-home exams. I 100% sure in some of the take-home exam, I will ask you to do finite difference. And I will ask you to do finite difference for multi-dimensional problems. That means you need to know those. Okay? When you do take-home exam, if you write a MATLAB code, ask computer to solve for you. I don't even know. It's okay. Because that's what I will do. But I still need you to write down things. So if you cannot write down those equations properly, when you write a computer code, there could be some mistakes. So eventually you need to know everything. Okay? What time is it? Oh, we still have a lot of time. Do you think it's enough today? Really? I can continue. Okay, let's do attendance check. Any questions? Okay, so let's do this. Okay, so Nikita, Yadev, Nikita Yadev, not here. Okay, this. Okay. Bini Yang. Okay, here. Feng Vi Lam. Okay. Lin Zhongwei. Okay. Liu Yijun. Okay. 陈品成 yeah. 许耀宗 yes. 文成汉 no. 肖立慈 okay. 陈伟燕 yeah. 胡甄嬛 yes. 曾伟志 yes. Duwanga yes. Okay. 王玉君 yes. 施燕如 oh, she was here, okay. So Emon, yes. Yang Junxiang, okay. 刘嘉伦 okay. 徐凯晴 yes. 林哲轩 okay. 喜荣 okay. Matthias, okay. Harry, yeah. Emre. Okay. 陈庭月. Yamro Kasanu. Okay, so you are not Emre. You are okay. Pronounce a little similar. I need to pronounce it properly. So you are. Let me find a way. How do people call you? How do people call you? Short name. Say again. Yamro. Okay, Yamro. So is Emre here? EMRE? Not here? Okay. Chen Tingyue, not here, right? Okay. Sohail? Ali? Sohail Ali? Okay. Who is missed?
I haven't broken, I think, because I wasn't there last week.
Okay. So, are you quitting or?
No, I wouldn't.
You want to join?
Yeah.
Okay. Thank you. So, I'm gonna give you two numbers. You're going to pick one. That's your teammate. So 5 and 13, choose one.
13.
Okay, so you are with Kai-Chin. That's your teammate. Okay. So what's your name?
Nelly Jung.
Nelly. How do you spell Nelly?
N-E-L-E.
N-E-L. Okay. So we're not sure if how many? 1, 2, 3, 4, 5. There are 5 students missing. So I hope they still come. If they are not here in the future, then we need to figure out. Jin, later on help me to send an email to the missing students. I need to make sure if they are coming, because it affects how we do the grouping. Okay. Any questions? Yeah, go ahead.
I still don't know my group.
You don't? Wen Chenghan is not here today. So what if he's dropping the course, then just individual research, that's fine. Because whoever has one teammate right now are students from my lab. So I don't want you to, work with someone you are familiar with. Okay, anyway, we'll see next week. Any other questions? Okay, maybe question? No? Let me try to know you guys more. Yang Junxiang, so you are, let me see, you are with Dewanga, right? So can I know which field are you in? Like a control, thermal? You are in Guli, solid mechanics. You are in solid mechanics. How about you? You're in control. So solid. Okay. But that's fine. That's perfect. He's an undergrad. You need to guide him more. So you are in control. Okay. So Matthias, You're a graduate student, right?
Undergraduate.
You're undergrad? Okay. So Yao Zhong, he's in my lab. So he's in solid mechanics robotics. So you guys can work on something like that. Yeah, Wen Chen Han is not here. Liu Yijun, undergrad, graduate. Solid mechanics. Okay, you're from solid mechanics. Okay. Xiao Lizi. Robotics. Okay. Feng Vi Lam. Solid mechanics. Okay. Binny Yang. You're from which field? Solid mechanics. Okay. Natho, is he here?
Yeah. Not tonight?
Si Yong.
Yeah, actually,
Oh, here.
yeah.
Which field are you in?
Certain mechanics.
Solid mechanics. Okay. Lin Zhongwei. Oh, you're also in solid. Okay. Harry.
I'm in solid mechanics.
You're in thermal.
Solid.
Solid. You're also in solid. Okay. Chen Weiyan. Robotics. Okay. Liu Jialun. Robotics. Okay. Nelly.
Yeah.
So which field are you in?
Mechanical engineering graduate with a, focus in applied mechanics.
Are you a mechanical? You're enrolled in our mechanical engineering, right? Do you have an advisor?
No, I'm just an
Undergrad. I change. Okay. No issues. That's good. Okay, so you're in any field.
Yeah.
Yeah, that's good. Okay, so most of our students are in solid mechanics and robotics. So this one in control. No thermal this time. Okay. There's no people from material science. Okay, that's good. Okay. So no more questions? I guess I can let you guys go because I didn't take a break. Okay, good. So please hand in your homework next time. When you come to a classroom, just put it here. Okay, you can please write down the solution. Okay, see you next time.
Similar course because it's like simulation.